Hi, everyone. Today we're starting chapter 13, which is all about solutions. We're going to learn what solutions are, why they matter in everyday life, and how we describe and work with them in chemistry. This chapter is especially important for future nurses like you because understanding solutions helps you understand IV fluids, blood composition, and medications. Let's dive in. In 1986, a tragedy occurred in Cameroon, West Africa, when carbon dioxide gas suddenly bubbled out of Lake Nyos and flowed into a nearby valley. This invisible gas displaced the oxygen in the air, suffocating over 1,700 people and 3,000 animals. The carbon dioxide had been trapped at the bottom of the lake, dissolved in the water under high pressure. When the water layers were disturbed, the pressure dropped and the gas escaped violently. This is a real-world example of how gases can dissolve in liquids and why understanding solutions can be a matter of life and death. Lake Nyos is located in a volcanic crater. Volcanic gases like carbon dioxide seep into the water from underground. Because pressure increases with depth, a lot of gas can dissolve in the deep water. Over time, the bottom layer became overloaded with gas. A small disturbance, like a landslide or temperature change, caused the gas to escape. Since CO2 is heavier than air, it flowed down and suffocated people and animals. This example shows how the solubility of gases is affected by pressure and helps us understand similar situations in hospitals and the body. To prevent another disaster, scientists installed a pipe system that slowly releases the carbon dioxide from the lake bottom. The controlled release creates a geyser and lets the gas out in small amounts so it doesn't build up dangerously again. This is a great example of how science and engineering can save lives and also how chemistry concepts like solubility and gas pressure are applied in real life. The water at the bottom of Lake Nyos was a solution, a homogeneous mixture of two or more substances. Homogeneous means the substances are mixed so well you can't tell them apart. Solutions are all around us: the ocean, soft drinks, blood plasma, and even the air we breathe. In a solution, one part is the solute, what gets dissolved, and one part is the solvent, what does the dissolving. In Lake Nyos, carbon dioxide was the solute and water was the solvent. Solutions can exist in many forms, not just liquid. You can have gas-gas solutions like air, liquid-liquid solutions like alcohol in water, solid-liquid like salt water, or even solid-solid like metal alloys. In nursing, most of what you'll deal with are liquid-based solutions like medications and IV fluids. But it's good to know that solutions come in different combinations. Every solution has at least two parts: the solvent, which is the main component, and the solute, which is the substance dissolved. Usually the solvent is the component in greater amount. In solid-liquid solutions, the liquid is almost always the solvent. Water is the most common solvent on Earth, especially in biological systems. That's why we call solutions in water aqueous solutions. Other solvents like alcohol or acetone are used in labs and industry. One of the most important rules in chemistry is like dissolves like. That means polar solvents dissolve polar solutes and nonpolar solvents dissolve nonpolar solutes. Water is polar, so it dissolves other polar substances like salt or sugar, but it doesn't dissolve nonpolar substances like oil. This is why oil and water don't mix. In nursing, you'll use this rule to understand how drugs dissolve in the body. For a solid to dissolve in water, the attractions between water and the solute must overcome the attractions within the solute and within the water. If the water can pull apart the solute molecules or ions and surround them, the solute will dissolve. This is how sugar or salt disappears when mixed into water. Here's how it works at the molecular level. Water molecules have positive and negative ends. The positive end is attracted to negatively charged ions and the negative end to positive ions. So when salt, NaCl, is added to water, the sodium plus ions are surrounded by the negative sides of water and the chloride minus ions are surrounded by the positive sides. The water molecules pull the ions apart and spread them out. This is what we mean by dissolving. When NaCl dissolves, the sodium positive and chlorine negative ions are completely separated and evenly dispersed in the water. Each ion is surrounded by water molecules in a stable way. That's why the solution looks clear and uniform. It's not just tiny salt particles floating around, it's individual sodium and chloride ions surrounded by water. This process is key for understanding how electrolytes work in the body. Solubility tells us how much solute can dissolve in a solvent at a certain temperature. If a solution holds as much solute as it can, like 36 grams of sodium chloride in 100 grams of water at 25 degrees Celsius, it's called a saturated solution. If you add more solute, it won't dissolve. If the solution has less solute than it can hold, it's unsaturated and can dissolve more. If somehow it holds more than the normal maximum, like under special pressure or cooling, it's called a supersaturated solution. That extra solute will eventually come out or precipitate. Remember Lake Nyos? When the CO2-rich water rose, the pressure dropped. The solution became supersaturated and the gas came bubbling out, causing tragedy. Another example is soda. When you open a can, pressure is released and carbon dioxide comes out. That's why you see bubbles. Some solids are very soluble and others are not. Table sugar is polar, so it dissolves well in water. But something like calcium carbonate, chalk, doesn't dissolve much because its internal ionic bonds are too strong. Similarly, nonpolar solids like fat or lard don't dissolve in polar water. This is why fat doesn't mix with your bloodstream unless it's broken down first. If a solute breaks into charged ions in water, it's called an electrolyte and it conducts electricity. Examples are salt, NaCl, and potassium chloride, KCl, which are vital in the body. If a solute stays as whole molecules, it's a non-electrolyte and doesn't conduct electricity like sugar. Nurses need to know which is which because IV fluids and medications can affect nerve signals and heart rhythms depending on their electrolyte content. In general, solids dissolve better in warmer water. That's why sugar dissolves faster in hot tea than in iced tea. This is useful when preparing medications or nutrient solutions. Sometimes warm water helps dissolve ingredients more quickly. Recrystallization is a way to purify solids. You dissolve a solid in hot water to make a saturated solution. Then as the solution cools, the solute comes out slowly in the form of crystals. Impurities stay dissolved, so the crystals that form are purer. This is a basic but powerful purification method. A fun example of recrystallization is rock candy. You heat water and dissolve sugar to make a saturated solution. Then you hang a string in it and let it cool. Over days, crystals grow on the string, creating rock candy. Chemistry can be sweet too. Let's now look at solutions where gases are dissolved in liquids. A soda can is a great example. Carbon dioxide is dissolved in water. Other examples include oxygen in lake water, which fish need to survive, and gases in our blood like oxygen and carbon dioxide. Even tap water contains tiny amounts of dissolved air. Unlike solids, gases dissolve better in cold water than in warm water. If you heat water, gases like oxygen and nitrogen start to come out. That's why you see tiny bubbles forming before the water even starts to boil. They're air bubbles, not steam. If you leave soda out and warm it up, it gets flat quickly. Why? Because gas solubility decreases with higher temperature. The carbon dioxide comes out of solution more quickly. Cold sodas keep the fizz better because the gas stays dissolved. Henry's law tells us that the solubility of a gas increases when the pressure of the gas above the liquid increases. This is why soda cans are pressurized. It keeps more CO2 in the liquid until you open the can. When you open a soda can, the pressure is released. As a result, the gas becomes less soluble and bubbles rapidly form and escape. That's the fizzing sound and rush of bubbles you see and hear. Mass percent is a way to measure concentration. It tells us how many grams of solute are in 100 grams of solution. So a 14% solution has 14 grams of solute in 100 grams of total solution. This method is often used in healthcare settings to describe things like saline concentration. Be careful, the denominator is the total mass of the solution, not just the solvent. We also use parts per million, ppm, and parts per billion, ppb, when dealing with very small concentrations, like in pollution or trace elements. We can use mass percent as a conversion factor. For example, if a solution is 8.5% CO2 by mass, we know that in every 100 grams of solution, there are 8.5 grams of CO2. This helps us calculate how much solute is in a given volume or mass of solution. Let's do a real example. If we have 28.6 liters of a solution that's 8.5% CO2 and has a density of 1.03 grams per milliliter, how many grams of CO2 are present? First, convert liters to milliliters, then use density to find the mass, and finally apply the mass percent. To solve, we start with volume in liters, convert to milliliters, then use density to find mass in grams, and finally multiply by 8.5% to get grams of CO2. This is how chemists calculate concentrations in real-world settings like water treatment and medical fluids. POPs, persistent organic pollutants, are harmful chemicals that enter our water through dumping or farming. They can build up in plants, animals, and eventually humans. This is why clean water is critical for health. POPs are nonpolar and get stored in fatty tissues. As small organisms eat contaminated material and bigger animals eat them, the chemical concentration builds up. This process is called bioamplification and can lead to severe health effects like cancer or nervous system damage. Molarity is another way to express solution concentration. It tells us how many moles of solute are present in 1 liter of solution. For example, a 1.0 m solution of sodium chloride has 1 mole of NaCl in 1 liter of water. This is important in medicine because many IV drugs are given based on molarity. To make a solution of a certain molarity, you measure the solute, like salt, and then add enough water to reach the desired total volume, not the other way around. That's key. Add water after you've added the solute to reach your final volume. Here's an example. Suppose we dissolve 15.5 grams of NaCl in enough water to make 1.5 liters of solution. To calculate molarity, convert grams to moles using the molar mass of NaCl, then divide by 1.5 liters. This gives you the molarity of the solution. Now let's use molarity to figure out how much of a compound is in a solution. Say we have 1.72L of 0.758 m sucrose solution. To find grams of sucrose, first calculate moles, volume times molarity, then convert moles to grams using the molar mass of sucrose. This type of calculation helps you figure out dosing or how concentrated a solution is. Being comfortable with molarity will help you read medication labels and lab reports with confidence. When ionic compounds dissolve, they split into ions. So the concentration of ions can be different from the concentration of the compound. For example, in a 1.0 m solution of CaCl2 calcium chloride, you actually get 1.0 m of calcium 2 plus and 2.0 m of chlorine minus. This is important for understanding electrolyte balance in the body. If you have 1.5 m Na3PO4 sodium phosphate, it splits into 3 Na plus and 1 phosphate ion PO4 with 3 negative charges per unit. That means you get 4.5 m of Na plus and 1.5 m of phosphate ions. Nurses need to understand this to interpret electrolyte panels. Sometimes we need to dilute a concentrated solution to make it safer or appropriate for use. The formula we use is M1V1 equals M2V2. This means molarity times volume of the concentrated solution equals molarity times volume of the diluted one. Why does this formula work? Because molarity times volume gives us moles of solute, and we want the number of moles to stay the same before and after dilution. This equation helps you decide how much water to add. Important safety tip: when diluting acids, always add acid to water, not the other way around. Adding water to acid can cause splattering and burns. This is a lab safety rule that's critical to remember. Let's say we have a 12.0 m stock solution of KCl potassium chloride, and we want to make 5.0 L of a 1.5 m solution. Plug the numbers into the dilution equation and solve for the volume of stock solution needed. This is practical chemistry used in pharmacy and hospital labs. This type of calculation is essential when preparing IV solutions or oral medications. Making the correct dilution keeps patients safe and ensures the medicine works as intended. Stoichiometry is about measuring amounts in a chemical reaction. In solution stoichiometry, we use the volume and molarity of a solution to calculate moles, then apply the balanced equation to find how much of another substance is needed or produced. The typical steps are: start with volume, convert to moles using molarity, then use the mole ratio from the balanced equation to find the amount of the other substance. This is useful in titration, which nurses may encounter in lab tests. Here's an example. How much 0.125 MnAOH do we need to neutralize 0.225 liters of 0.175 MH2SO4? Use molarity times volume to get moles of H2SO4, then multiply by 2 because each H2SO4 has 2 hydrogen plus ions, and solve for volume of NaOH. You finish the calculation by dividing the moles of NaOH needed by its concentration. This gives you the volume required. These kinds of stoichiometry calculations are essential in clinical labs. Colligative properties depend on the number of solute particles, not what the particles are. These include freezing point depression and boiling point elevation. When you add salt to water, it boils at a higher temperature and freezes at a lower one. When a solute is added to a solvent, it disrupts the freezing process. That's why salt is spread on icy roads. It lowers the freezing point of water so it stays liquid even when it's cold. This is called freezing point depression and is calculated using molality. Let's work through a freezing point depression example. Imagine we dissolve 17.2 grams of ethylene glycol, a common antifreeze, into 0.500 kilograms of water. First, we convert the mass of ethylene glycol into moles using its molar mass. Then we calculate molality by dividing moles of solute by kilograms of solvent. This gives us the concentration needed for freezing point calculations. Let's say we have a 1.7 molal M ethylene glycol solution. The freezing point depression formula is DTF equals M times KF, where KF is the freezing point depression constant for water. Water normally freezes at 0 degrees Celsius, but this solution might freeze at 3 degrees Celsius or lower depending on the calculation. Just as freezing point goes down, the boiling point goes up when a solute is added. In hot climates, antifreeze prevents engine coolant from boiling over. It raises the boiling point, keeping fluids stable even when it's hot. The formula for boiling point elevation is dTB equals M times Kb, where dTB is how much the boiling point increases, M is molality, and Kb is a constant specific to each solvent. For water, we use a standard Kb value. For a 1.7 M ethylene glycol solution, use the equation to calculate the change in boiling point. Then add that to 100 degrees Celsius, water's normal boiling point, and you get the boiling point of the solution. Wood frogs survive freezing winters by producing glucose, which acts like antifreeze. It lowers the freezing point inside their cells so they don't freeze solid. Their heart stops and they appear dead, but they revive when warmed up. Nature uses chemistry in amazing ways. Osmosis is when water flows from a less concentrated area to a more concentrated one. This is why drinking seawater makes you more dehydrated. The high salt content pulls water out of your body's cells. In an osmosis setup, water moves through a semi-permeable membrane from a dilute to a concentrated solution. This can be seen in labs and also in how cells react to different environments. In your body, if cells are surrounded by salt water, they lose water and shrink. In pure water, they absorb water and swell. Understanding this helps nurses manage IV fluids properly. The pressure that builds up as water moves across the membrane is called osmotic pressure. The more concentrated the solution, the higher the osmotic pressure. This is another colligative property. Red blood cells are sensitive to osmotic pressure. In pure water, they swell and may burst. In concentrated salt solutions, they shrink. In an isoosmotic solution, same concentration as the cell, they stay normal. This is why IV solutions must be carefully prepared. We classify solutions based on how they compare to body fluids. Hypoosmotic, too dilute, hyperosmotic, too concentrated, and isoosmotic, just right. IV solutions must be isoosmotic, like 0.9% saline, to avoid harming cells. Solutions are homogeneous mixtures. Solubility depends on temperature and pressure. Solids generally dissolve better in warm water, gases dissolve better under high pressure and in cold temperatures. We express concentration using mass percent, molarity, and molality. When diluting solutions, we use the M1V1 equals M2V2 formula. These concepts are essential in preparing medications and IV fluids. Colligative properties depend on the number of solute particles, not their type. These include boiling point elevation, freezing point depression, and osmotic pressure, all of which impact the body and medical treatments. By now, you should be able to calculate mass percent, molarity, and molality, use these values in real calculations, understand dilution and stoichiometry, and explain key colligative properties like boiling and freezing point changes and osmosis. These are foundational concepts for safe, effective nursing practice. Great job today!